Waves are a series of disturbances which propagate from a source to the surroundings or a destination. They carry along with them a certain amount of energy and information in the form of signals. Let us consider an example where a pebble is thrown into a pond of still water. We see ripples formed at the place where the pebble touches the surface of the water and move outward in circles. A dry leaf on the surface of the water is seen moving up and down in its place. This shows that the water does not move along with the wave. This disturbance in the medium, that is, water, is transmitted from particle to particle. This is due to the elastic forces binding them. Waves not only propagate through liquids, they also propagate through solids and gases. Now, let us look at various other examples where waves propagate through other media. In today's world, communication systems play a vital role. These communication systems involve the transmission of waves to send and receive information. For example, while communicating through a telephone, the sound waves produced by the vocal cords are converted into electrical waves or signals at the source. These electrical signals can be processed in different ways to reach the receiving end. These electrical signals may be transmitted through a copper cable, converted into light signals, and then transmitted through optical cables, converted into electromagnetic waves, and then transmitted through air or communication satellites. The signals received are converted back to sound waves by an instrument at the receiving end. It is not only solids, liquids and gases. Waves can also travel through a vacuum. For example, sunlight travels through a vacuum before it reaches the Earth's atmosphere. Waves are classified into three types: mechanical waves, electromagnetic waves, and matter waves. Mechanical waves are governed by Newton's laws and need a medium to propagate, that is, solids, liquids, and gases or air. Waves in water, sound waves, and seismic waves are some examples of mechanical waves. Electromagnetic waves do not require any medium for propagation. They can travel through a vacuum too. They travel with a speed of nearly 3 × 10⁸ meters per second. Light waves, ultraviolet light waves, radio waves, microwaves, and X-rays are some examples of electromagnetic waves. Matter waves are associated with moving electrons, protons, neutrons, and other fundamental particles. The electron microscope works on the principle of the motion of electrons, thereby constituting matter waves. Let us now discuss mechanical waves in detail. Waves in elastic media, that is air, stretched springs, coil springs, etc., are intimately connected with harmonic oscillations, which constitute mechanical waves. To understand this better, let's consider the example of a slinky. When one end of the slinky is fixed and a slight disturbance is created at the free end, we observe the disturbance carried to the fixed end of the slinky. Now, let us see how sound waves propagate through air. When a sound is produced, it compresses or expands a small region of air at the source, causing a change in the density delta rho of the air in the region. This induces a change in the pressure delta P of air in that region. The pressure causes compressions in the particles surrounding the source. These particles in turn transmit pressure to neighboring particles, which are now compressed due to this pressure. After the transmission of pressure, the particles near the source return to their original positions. This is due to the restoring force of the elastic medium, that is, air. Thus, in the region of compression, an expansion of the air layers takes place. Therefore, a series of compressions and expansions or rarefactions in the region of transmission is observed. Mechanical waves can be either transverse or longitudinal. This depends on the relationship between the direction of displacement of the particles in the medium and the direction of the propagation of the disturbance or the wave. In a transverse wave, the particles of the medium vibrate in a direction normal to the direction of the propagation of the wave. In a longitudinal wave, the particles of the medium vibrate in a direction parallel to the direction of the propagation of the wave. In both waves, it is only the disturbance that propagates and not the particles of the medium. The particles of the medium only vibrate about their main positions. Let us conduct an experiment to understand how a transverse wave is produced and propagated. Let us first fix one of the ends of a string of length 5 meters to a pole. Hold the free end of the string tight so that the string is taut. Now let's jerk the string by moving the hand up and bringing it back to its initial position. The pulse that is created by the jerking action traverses through the string to the fixed end and dies down. The movement of the pulse through the string can be compared to the movement of a caterpillar. The pulse that traverses through the string moves with a certain velocity v. Next, when the hand is moved up and down continuously about the mean position with a simple harmonic motion, a continuous wave, which is sinusoidal in shape, travels along the string with a velocity v. There are two ways to study the wave formed in this process. The first one is by taking a snapshot of the string while the waves are traveling through it. The other method is by marking a point on the string and observing it as the waves propagate through the string. We see that the point moves up and down the mean position. The waveform observed in this process, which is sinusoidal in shape, is a transverse wave. Let us now conduct another experiment to understand how a longitudinal wave is produced and propagated. The apparatus required to conduct this experiment is a long glass tube with an airtight piston at one end. Air with lots of dust particles is trapped inside this tube. Now, let us place this tube in a dark room with a focus light behind the tube. The piston is pushed inside the tube and pulled back with a jerk. We now observe that the dust particles near the piston are compressed and form a band. This is due to an increase in pressure created by the piston on the particles. This band, called compression, moves towards the other end of the tube as a pulse and dies down. When the piston is pulled back, we observe that the pressure at the compressed region decreases and causes the dust particles to move back to their original position. The low pressure region formed is called rarefaction. Now let us move the piston forward and backward about a mean position with a simple harmonic motion. We see a series of compression and rarefaction bands formed by the dust particles inside the tube, moving towards the other end. These bands constitute longitudinal waves. In a transverse wave, as the wave propagates, each element of the medium undergoes a shearing strain. Elements in solids and liquids have the capacity to undergo a shearing strain. Therefore, transverse waves can propagate through solids and liquids. Transverse waves on the surface of still water are called capillary waves, whose wavelength measures in centimeters only. The restoring force that allows the propagation of these waves is the surface tension of water. Waves formed on the surface of the sea are transverse waves, called gravity waves, whose wavelength is of the order of meters. The restoring force in these waves is the gravitational pull on the water. In a longitudinal wave, as the wave propagates, each element of the medium undergoes a compressive strain. The elements in solids, liquids, and gases have the capacity to undergo a compressive strain. Therefore, a longitudinal wave can propagate through solids, liquids, and gases. During the propagation of a wave through a medium, all the particles of the medium vibrate about a mean position with simple harmonic motion. The displacement of a particle from its mean position at any given time depends on its position with respect to the origin of the wave. This displacement is represented as y of x, t, and is calculated with the help of the four parameters of the waveform: amplitude A, propagation constant or angular wave number k, angular frequency omega, initial phase angle phi, Using the equation y of x t is equal to a into sine kx minus omega t plus phi, where y is the displacement of the particle in the y direction, and x is the x-coordinate of the particle, and t is the time lapsed from the origination of the wave. The displacement equation of the particle is expressed as y of x t is equal to a into sine kx minus omega t plus phi. This equation represents a progressive wave traveling along the positive direction of the x-axis. That is, from left to right. To represent a progressive wave traveling along the negative direction of the x-axis, that is, from right to left, the equation is y of x t is equal to a into sine kx plus omega t plus phi. These equations are obtained from the harmonic circle. A particle is moving in a circular path of radius a, which is the amplitude of the wave, and occupies a position P. The line joining the origin O and P makes an angle theta with the positive side of the x-axis. Drop a perpendicular from P onto the x-axis at point Q. QP represents the displacement of the particle in the y direction. In the triangle POQ, sin theta is equal to y by a. By cross multiplying, we get y is equal to a sin theta. The particles in the medium vibrate with a simple harmonic motion to propagate the wave. Let us consider a point P moving along a circular path with constant angular velocity omega radians per second. Take the projection of this point P on the time meter parallel to the y-axis to obtain the point P dash. As P moves around the circular path, P dash will be moving up and down along the diameter with simple harmonic motion. When the positions of a number of adjoining particles in a medium which are vibrating with SHM are plotted, we get a sinusoidal curve. We can observe a moving sinusoidal waveform by performing a simple activity. Fix one end of a string of length, say 5 meters, to a wall. Hold the free end of the string tight so that the string is taut. When the hand is moved up and down continuously about the mean position with a simple harmonic motion, a continuous wave, which is sinusoidal in shape, travels along the string with the velocity v. Let us mark a point on the string and observe it as the wave propagates through the string. We see that the point moves up and down the mean position. The waveform observed in this process, which is sinusoidal in shape, is a transverse wave. The wave travels in the positive direction of the x-axis. The points of maximum positive displacement are called crests, and the points of maximum negative displacement are called troughs. The maximum displacement of the particles from their equilibrium or mean positions as the wave passes through them is called the amplitude A. As A represents only the magnitude, it is always a positive quantity even if the displacement is in the negative direction. initially. That is, at x is equal to 0 and t is equal to 0. The particle may have positive, negative, or zero displacement in the y direction. When the particle has positive or negative displacement, we say it has positive or negative initial phase angle phi corresponding to the position on the harmonic circle. Wavelength lambda of a wave is the distance in the x direction between any two consecutive repetitions of the shape of the wave. It is the distance between two consecutive troughs or crests, or two consecutive points in the same phase of wave motion. Coming to the propagation constant of the angular wave number k of the wave, consider a sinusoidal wave curve with conditions phi equal to 0 and t equal to 0. Substituting these values in the equation of the progressive wave traveling along the positive direction of the x-axis, that is, y of xt is equal to a into sine kx minus omega t plus phi. Let this be equation 1. It gives y of x 0 is equal to a into sine kx. Let this be equation 2. Let us mark 2 points P and Q which are at the same phase on the wave. Point P is at a distance x1 from the origin, and Q is at a distance x2 from the origin. When equation 2 is applied at points P and Q, at point P, we get y1 of x1 and 0 is equal to a sine k into x1. Let this be equation 3. And at Q, we get y2 of x2 and 0 is equal to a sine k into x2. Let this be equation 4, where y1 is the displacement at P on the y-axis, and y2 is the displacement at Q on the y-axis. As P and Q are in the same phase, they are separated by a distance of one wavelength, that is, lambda. Therefore, y1 is equal to y2. We can now equate the right-hand sides of equations 3 and 4. A sine kx1 equal to a sine kx2. By substituting x2 is equal to x1 plus lambda, we get a sine kx1 is equal to a sine k into x1 plus lambda. This can be written as a sine kx1 is equal to a sine into kx1 plus k lambda. This condition is possible only when k lambda is equal to the product of 2, pi and n, where the values of n are equal to 1, 2, 3 and so on. We have defined lambda as the least distance between 2 points in the same phase. Therefore, for the least value of n, that is 1, k lambda is equal to 2 pi. K is equal to 2 pi by lambda. Therefore, the propagation constant or the angular wave number k is denoted by k is equal to 2 pi by lambda radians per meter. The SI unit of angular wave number k is radians per meter. As radians are only a number, usually units of k are written as the value per meter. Let us now discuss the period, angular frequency, and the frequency of a wave. Consider the equation y of x t is equal to a sine into kx minus omega t plus phi. Let this be equation 1. By substituting x is equal to 0 and phi equal to 0 in equation 1, we get y of 0t is equal to a sine into minus omega t. This equation can be written as y of 0t is equal to minus a sine into omega t. Let this be equation 2. Points P and Q are at the same phase. That is, one oscillation is completed between points P and Q, and the time taken for this oscillation is called period of oscillation t of the wave. Substituting the x-coordinate values of t at points P and Q in equation 2, at point P, we get y1 of 0 t1 is equal to minus a sine omega t1. At point Q, we get y2 of 0 t2 is equal to minus a sine omega t2. And equating their right-hand sides, we get minus a sine omega t1 is equal to minus a sine omega t2. That is, their displacement will be same as they are at the same phase. The particle of the medium has completed one oscillation from point P to point Q, for which the time taken is the time period t. By substituting t2 equal to t1 plus t, we get minus a sine omega t1 is equal to minus a into sine omega into t1 plus t. This equation can be written as minus a sine omega t1 is equal to minus a sine into omega t1 plus omega t. Let this be equation 3. The above equation is true only if omega t is equal to 2 pi. Therefore, omega is equal to 2 pi by t. This omega is known as the angular frequency of the wave. Omega is also the angular velocity of the point moving along the harmonic circle, from which the sinusoidal wave has been generated. The SI unit for angular frequency omega is radians per second. Frequency is the number of oscillations per unit time made by a particle as the wave passes through it. It is represented by the Greek letter nu and is measured in hertz. Frequency is denoted by the equation mu is equal to 1 by t, which is equal to omega by 2 pi. In longitudinal waves, the particles are displaced in the direction of motion of the wave. The displacement equation is written as S of x t is equal to a sine into kx minus omega t plus phi, where S of x t represents the displacement of the particle in the direction of propagation of the wave at position x and time t. Let us consider a propagating wave that is generated on a stretched string. The initial conditions at the origin are time t is equal to 0, x coordinate x is equal to 0. Y coordinate y is equal to 0 and phase angle of the wave phi is equal to 0. Let us mark a point A on the string. After a time t, the wave has travelled a distance x and the particle A is situated at a distance x from the origin and is now at the crest of the wave. We take a snapshot 1 with a high-speed camera showing the waveform. After an additional time delta t, we take another snapshot 2 and mark point B on the crest of the progressive wave. The crest, which was at particle A, has now moved to particle B. Particle B is situated at x plus delta x from the origin O. Now, let's superimpose the two snapshots. During the time interval delta t, the waveform has moved through a distance delta x. Therefore, the speed of the wave is denoted by delta x by delta t. We have discussed particles A and B, which were in the same phase, that is, the crest of the progressive wave. Now, let's take another pair of elements, say C and D, which are at the same phase. We find that their displacement in the y direction is also the same. Since the wave is travelling along the positive direction of the x-axis, that is, from left to right, the waveform can be represented by the expression y x t is equal to a into sine kx minus omega t plus phi, where k is the angular wave number and omega is the angular frequency of the wave. From the initial conditions, we know that phi is equal to 0. Therefore, yxt is now equal to a into sine kx minus omega t. For particles C and D, y is the same. Therefore, kx minus omega t is a constant. Let this be equation 1. As the wave propagates, the values of x and t between particles C and D are changing. So, to keep the value of k x minus omega t as constant, as x increases, t should also increase. To find the speed of the wave v, we differentiate equation 1 with respect to time t. On further simplifying, we get dx by dt is equal to omega by k, where dx by dt represents the velocity v of the wave. Therefore, v is equal to omega by k. Let this be equation 2. Substituting omega equal to 2 pi by t and k equals to 2 pi by lambda in equation 2, where lambda is the wavelength of the wave, we get v is equal to 2 pi by t by 2 pi by lambda. This is equal to lambda by t. Let this be equation 3. Equation 3 can be written as v is equal to lambda into 1 by t. Substituting frequency nu is equal to 1 by t in the above equation, we get the speed of the wave v is equal to lambda into nu. Let this be equation 4. The speed of a progressive wave is related to wavelength lambda and frequency nu as given in equation 4. As a wave travels through a medium, the particles of the medium have to oscillate or vibrate. Any vibrational phenomenon is associated with mass and the elasticity of the particles of the medium. Therefore, mass per unit length for strings and the elastic property of the material medium determine how fast a wave can travel through the medium. Let us derive an expression to calculate the speed of a transverse wave on a stretched string. The speed of the transverse wave on a string depends on mass per unit length of the string, mu, the tension of the string, T, a relationship between speed of the wave v, mass per unit length of the string, mu, and tension T of the string can be derived by the dimensional analysis method. Let the mass of the string be m and the length of the string be L. The linear mass density mu of the string is equal to mass by length. Therefore, the dimensions of mu are m into L raised to the power minus 1. Tension T in the string is equal to the applied force N. Force is the product of mass and acceleration. Substituting, the dimensions of A are equal to the product of L and T raised to the power minus 2 in the above equation. This is equal to the product of M, L, and T raised to the power minus 2. Therefore, the dimensions of tension T are M, L, and T raised to the power minus 2. Velocity is expressed in meters per second. Hence, velocity can be equated to L into T raised to the power minus 1. Therefore, the dimensions of velocity are L into T raised to the power minus 1. Let us now find the dimensions of T by mu to arrive at the dimensions of V square by substituting the dimensions of T and mu. And simplifying, we get T by mu is equal to the product of L square and T raised to the power minus 2. Let this be equation 1. The RHS of the equation 1 has the dimensions of V square. Therefore, we can write T by mu is equal to V square. On further simplifying, V is equal to C into root T by mu, where C is a dimensionless constant. This dimensionless constant C has been proved to be equal to 1. Therefore, V is equal to the square root of T by mu. This proves that the speed of a wave along a stretched string depends only on the tension and the linear mass density of the string, and not on the frequency of the wave. The frequency of the wave is the frequency of the source which generates the waves. The wavelength lambda is determined by the ratio of velocity v and frequency nu. A steel wire 1 meter long has a mass of 8 grams. If the wire is under a tension of 100 Newton, what is the speed of the transverse waves on the wire? Mass per unit length mu is expressed as 8 into 10 raised to the power minus 3 divided by 1 kilogram per meter. Let v be the velocity of the wave. Velocity is expressed as the square root of tension T of the wire by mass per unit length mu. By substituting the values of T and mu, we get V is equal to the square root of 12,500, which is equal to 111.8 meters per second. Therefore, the speed of the transverse wave through the steel wire is 111.8 meters per second. Sound waves, which are longitudinal waves, propagate with the vibrations of the particles of a medium in the direction of propagation of the waves. Sound waves in air consist of propagating compressions and rarefactions of small volume elements of air. In the region of compressions, there is an increase of pressure delta P, due to which the volume V of the elemental volume decreases by delta V. The volumetric strain of the elemental volume is denoted by the ratio between delta V and V. Bulk modulus B is expressed as the change in pressure by volumetric strain, which is equal to minus delta P by delta V by V. Let this be equation 1. The SI unit of pressure is Newton per meter square or Pascal. The dimensional units of pressure P are kilogram meter per second square into meter raised to the power minus 2. That is, the product of m, L, T raised to the power minus 2 and L raised to the power minus 2. Dimensional units of change in the pressure delta P is equal to the product of m, L raised to the power minus 1 and T raised to the power minus 2. Let this be equation 2. In the region of compressions, there is an increase of pressure delta P. There is a decrease in volume delta V and an increase in density. The dimensional units of density are kilogram per meter cube. That is, the product of m and L raised to the power of minus 3. Let this be equation 3. Let us now find the dimensions of bulk modulus B by density ρ to arrive at the dimensions of velocity V. From equations 2 and 3, we get B by ρ is equal to m, L raised to the power minus 1 and T raised to the power minus 2 by mL raised to the power minus 3. B by ρ is equal to the product of L square and T raised to the power minus 2. This can be written as L into T raised to the power minus 1 whole square, which are the dimensional units of V. Therefore, V can be written as the product of C and root B by ρ, where C is a dimensionless constant, which is equal to 1. This can be written as V is equal to the root of B by rho. Let this be equation 4. Equation 4 implies that the speed of a longitudinal wave in a fluid depends only on the bulk modulus and the density of the fluid. Instead of a fluid, if you consider a solid bar as the medium, Young's modulus Y is used in place of bulk modulus B, as sideways compression or expansion of the bar is negligible. Only longitudinal strain is considered and the equation is modified to V is equal to root Y by rho. Let this be equation 5. The table shows the speed of sound in various media. From this table, we find that the speed of sound in liquids and solids is higher than in air. The reason is that the densities of liquids and solids are higher than the density of air. Liquids and solids are less compressible than air, and therefore have a greater bulk. Liquids and solids are less compressible than air, and therefore have a greater bulk modulus, resulting in a higher value of B by rho. Newton tried to find the speed of sound in an ideal gas. Assuming that the gas undergoes isothermal changes while a sound wave propagates through it. Isothermal refers to equal thermal conditions, meaning a constant temperature that is maintained while energy propagates through the gaseous medium. For an ideal gas, under isothermal conditions, the relationship between pressure P and volume V is expressed as PV is equal to the product of NKBT, where N is the number of gas molecules in volume V. Kb is the Boltzmann constant, and T is the absolute temperature of the gas. The quantities on the right-hand side of the equation are constant. Hence, PV is equal to constant. The above expression leads to delta PV is equal to 0. This implies that V delta P plus P delta V is equal to 0. This can be written as V delta P is equal to minus P delta V. V delta P by delta V is equal to minus P. Once again, this equation can be written as delta P by delta V by V is equal to minus P. Therefore, minus delta P by delta V by V is equal to P. The left-hand side of the above expression is nothing but the bulk modulus B of the gas. Substituting this in the equation for the velocity of sound in air, V is equal to root P by rho. Let this be equation 6. Thus, the speed of a sound wave in an ideal gas is denoted by equation 6. As this equation was given by Newton, it is called Newton's formula. Let us now calculate the velocity of sound in air using Newton's formula. The density of air is the product of the mass of 1 mole of air and its volume. Let this be equation 1. Mass of 1 mole is 29 into 10 raised to the power minus 3 kilograms. And its volume is 22.4 into 10 raised to the power minus 3 meter cube at standard temperature and pressure. By substituting the values in equation 1, we get rho is equal to 1.29 kilograms per meter cube. We know that atmospheric pressure P is equal to 1.01 into 10 raised to the power 5 Newton per meter square. Substituting the values of 2 and 3 in Newton's formula, we get the velocity of sound in air at standard conditions of temperature and pressure, according to Newton's formula, is V is approximately equal to 280 meters per second. But the experimental value of the velocity of sound in air at standard temperature and pressure conditions is nearly 331 meters per second. This means the value derived from Newton's formula is about 15.4% less than the experimental value. This variation in magnitude in the experimental value and the calculated value cannot be attributed to experimental errors. Hence, there arose a need to revisit Newton's assumptions on deriving the expression for velocity of sound in gases. It was Pierre-Simon Marquis de Laplace, a French mathematician and astronomer, who pointed out that the speed of sound in air depends on the heat capacity ratio. This is because the changes that take place in air or any gaseous medium while sound propagates through it is adiabatic and not isothermal as assumed by Newton. Adiabatic change is a change that takes place without the exchange of heat. Sound propagates in the form of compressions and rarefactions. Compression leads to heating and expansion leads to cooling as the sound propagates through the gas. Laplace pointed out that pressure variations in the propagation of sound waves are so fast that there is little time for the heat flow to maintain a constant temperature. Hence, these variations in pressure are adiabatic and not isothermal. For an adiabatic process, the ideal gas satisfies the relation P into V raised to the power of gamma, which is a constant, where P and V are the pressure and volume of the gas. Gamma is the ratio of specific heat capacities, ratio of specific heat at constant pressure Cp to that of specific heat at constant volume Cv. Cp by Cv of the gas. The above equation leads to delta P into V raised to the power of gamma equals to 0. This implies that P into gamma into V raised to the power gamma minus 1 into delta V plus V raised to the power gamma into delta P is equal to 0. This equation can be written as the product of P, gamma, V raised to the power gamma minus 1 and delta V equal to minus V raised to the power gamma into delta P. Therefore, P into gamma is equal to minus V raised to the power gamma into delta P by delta V into V raised to the power gamma minus 1. On further simplifying, we get P into gamma is equal to minus delta P by delta V by V. Thus, the bulk modulus of the gas is P gamma, and not just P, as Newton arrived at while deriving the expression. Thus, the velocity of sound in an ideal gas, after Laplace's correction, is expressed as V is equal to the root of gamma P by rho. Let this be equation 1. The value of gamma for air is 1.4. Substituting the values of gamma, P and rho for air in equation 1, we get the value of sound V in air as approximately equal to 331 meters per second. The speed of sound in air at standard temperature and pressure conditions thus obtained implementing Laplace's correction is in agreement with the experimental value. Let us consider two pulses traveling simultaneously along the same stretched string in opposite directions. The net displacement of any element of the string as the two pulses cross each other is the algebraic sum of the displacements due to each pulse. After crossing each other, the pulses move forward unchanged. The addition of the waveforms or pulses to find the net or resultant waveform is known as the principle of superposition. Y1 of xt represents the displacement of any element of the string at time t due to the first wave. Y2 of xt represents the displacement of any element of the string at time t due to the second wave. Let us now consider two waves traveling simultaneously along the same stretched string in opposite directions. When the two waves overlap, we have y of xt representing the displacement of the string in the overlap region at time t. Mathematically, we can write this as y of xt is equal to y1 of xt plus y2 of xt. This expression implies that overlapping waves algebraically add up to produce the resultant wave. Let us consider an example to observe the effect of the superposition of waves. When the waves are propagating in the same direction along a stretched string, both the waves have the same angular frequency, omega, and angular wave number, k, as they are propagating on the same string. They have the same amplitude, a. Their phases at a given x and t differ by a constant angle phi. By changing the angle phi, we can observe different net waveforms. That is, when phi is equal to 0, we find that the amplitude of the net waveform is doubled. When phi is equal to pi, the two waves are completely out of phase, and therefore the amplitude of the net waveform reduces to 0. And we get a straight line. When the value of phi is between 0 and pi, the amplitude of the net waveform keeps changing from 2a to 0, where a is the amplitude of the original waveform. The net waveform shifts by phi divided by 2. These observations can now be expressed mathematically. The first wave is represented by y1 of xt is equal to a into sine kx minus omega t. Let this be equation 1. The second wave is represented by y2 of xt is equal to a into sine kx minus omega t plus phi. Let this be equation 2. The second wave is shifted by a phase angle phi from the first wave. From equations 1 and 2, we can say that both waves have the same angular frequency omega, the same angular wave number k, and the same wavelength lambda. The velocity of the waves propagating on a single stretched string is same. This is because the velocity of the wave on a stretched string depends only on the tension T in the string and its linear mass density mu. The velocity of the wave is expressed as the root of the ratio between T and mu. And in one stretched string, T and mu are constant. Now we can apply the principle of superposition of waves to arrive at the expression for the resultant waveform. By adding equations 1 and 2, we get y of xt is equal to a into sine kx minus omega t plus a into sine kx minus omega t plus phi. Let this be equation 3. Let us consider the trigonometric relation, which is similar to equation 3. Let this be relation 4. Applying relation 4 to equation 3, we get y of xt is equal to 2a cos phi by 2 into sine kx minus omega t plus phi by 2. Let this be equation 5. From equation 5, we find that the resultant wave is also a sinusoidal wave, which is propagating in the positive direction. There are two differences between the resultant wave and the constituent waves 1 and 2. The resultant wave has a phase angle equal to half of phi with respect to the first wave. The amplitude of the resultant wave is equal to 2a cos phi by 2. We can now apply these mathematical expressions to compare with our actual observations. When phi is equal to 0, the amplitude of the resultant wave is equal to 2a. And the two waves are in phase. And equation 5 becomes y of xt is equal to 2 into a sine kx minus omega t. Let this be equation 6. Comparing equations 1, 2, and 6, we find that the amplitude of the resultant wave is equal to twice the amplitude of the constituent waves 1 and 2. When phi is equal to pi, the two constituent waves are completely out of phase, and equation 5 becomes y of xt is equal to 0. Let this be equation 7. Equation 7 indicates that the resultant wave has 0 amplitude. That is, the wave is a straight line. When a pulse of a traveling wave strikes a rigid boundary, it gets reflected. An echo is one of the simplest examples of this phenomenon. If the boundary is not completely rigid, or if it is an interface between two different elastic media, a part of the wave is reflected, and a part is transmitted into the second medium. Reflection of waves follows the laws of reflection, which are similar to the laws of reflection of light. To understand the phenomenon of reflection of waves, let us perform two simple activities. In the first activity, the left end of a string is fixed to a rigid wall. In the second activity, the left end of the string is tied to a ring which can slide up and down without any friction on a rod. A single pulse is generated at the free end of the strings. In the case of the first activity, the pulse, on reaching the left end of the string, encounters the rigid wall. The pulse applies an upward pull on the wall, and the wall applies an equal but opposite downward pull on the string, obeying Newton's third law of motion. The downward pull by the wall on the string generates a pulse which travels in a direction opposite to that of the incident pulse. As there is no displacement of the particle at the junction of the string and the wall, the incident and reflected pulses have opposite signs and cancel each other at that point. Due to this phenomenon, the reflected pulse has a phase reversal or a phase difference of pi or 180 degrees. In the second activity, when the pulse reaches the end of the string, it pulls the ring up. As the ring moves up, it pulls the string, producing a reflected pulse with the same sign and amplitude as the incident pulse. In this process, the incident and reflected pulses reinforce each other, creating maximum displacement at the end of the string. The reflection is without any additional phase shift. Let us now express these observations mathematically. The incident wave is represented by yi of x t is equal to a sin kx minus omega t, where a is the amplitude and k is the wave number of the wave. The reflected wave from a rigid boundary is represented by yr of x t is equal to a sin kx plus omega t plus pi, which is equal to minus a sin kx plus omega t. For the reflection at an open boundary, the reflected wave is represented by yr of x t is equal to a sin kx plus omega t. When a wave is incident obliquely on the boundary between two different media, we know that a part of it is reflected and a part is transmitted to the second medium. This transmitted wave is called the refracted wave. Refraction of waves follows Snell's laws of refraction, as in the case of a beam of light. Let us consider a system bounded at both the ends, such as a stretched string fixed at both the ends. Let us generate a continuous sinusoidal wave of a certain frequency moving to the right. This wave can be represented by y1 of x t is equal to a sin kx minus omega t. Let this be equation 1. This wave, on reaching the right end, gets reflected and travels to the left. This reflected wave can be represented by y2 of xt is equal to a sin kx plus omega t. Let this be equation 2. The reflected wave, on reaching the left end, gets reflected again and travels to the right. This process of reflection continues endlessly. At any point x and at any time t, there are always two overlapping waves, one moving to the right and the other moving to the left. By superimposition of waves 1 and 2, we get a combined wave which can be represented by y of xt is equal to y1 of xt plus y2 of xt. Let this be equation 3. On substituting 1 and 2 in equation 3, we get y of xt is equal to a sin kx minus omega t plus a sin kx plus omega t. This equation can be written as y of xt is equal to 2a into sin kx into cos omega t. Let this be equation 4. In equation 4, 2a into sin kx represents the amplitude of oscillations of an element of the string located at position x. Note that this amplitude changes with x. Whereas, in a traveling wave, the amplitude of the wave is the same for all the elements of the string. Therefore, equation 4 represents a standing wave and not a traveling wave. Let us now find the positions of the elements of the stretched string where the amplitude of the standing wave is 0. The standing wave is represented by y of xt is equal to 2a into sine kx into cos omega t. For amplitude to be 0, 2a into sine kx has to be equal to 0. Let this be equation 1. As a cannot be 0, sine kx has to be equal to 0. This means kx is equal to n into pi. Let this be equation 2. And the values of n are equal to 0, 1, 2, and so on. We know that k is equal to 2 pi by lambda. Substituting k is equal to 2 pi by lambda in equation 2, we get x is equal to n lambda by 2 for n is equal to 0, 1, 2, 3, and so on. X gives the positions of 0 amplitude of the resultant standing wave. The positions of 0 amplitude are called nodes. The distance between any two consecutive nodes is lambda by 2. Now, let us find the position of the elements of the stretched string, where the amplitude of the standing wave is maximum. The standing wave is represented by y of xt is equal to 2a into sine kx into cos omega t. Amplitude is equal to 2a into sine kx. When mod sine kx is equal to 1, the maximum possible amplitude is 2a. For mod of sine kx is equal to 0, kx is equal to n plus 1 by 2 into pi. For n is equal to 0, 1, 2, and so on, we know that k is equal to 2 pi by lambda. Substituting the value of k in the above equation, we get 2 pi by lambda into x is equal to n plus 1 by 2 into pi. By rearranging the above equation, we get x is equal to n plus 1 by 2 into lambda by 2. For n is equal to 0, 1, 2, and so on. Let this be equation 1. Equation 1 gives the position of maximum amplitude of the resultant standing wave. These positions are called the antinodes. The distance between two consecutive antinodes is lambda by 2. They are located midway between two consecutive nodes. We will now discuss harmonics. Let us consider a stretched string that is fixed at both ends and plucked to generate a wave. Notes are produced at both the fixed ends. If the left end of the string is taken as the origin, then for the right end x is equal to L, where L is the length of the string. For the right end to be a node, the length L is equal to n into lambda by 2. For n is equal to 1, 2, 3, and so on. On rearranging the above equation, we get lambda is equal to 2L by n. For n is equal to 1, 2, 3, and so on. Let this be equation 1. Equation 1 shows that the standing waves on a string of length L have restricted wavelength. We know that the velocity of the wave v is equal to lambda into nu. Where nu is the frequency of the wave, v is the velocity of the wave, and lambda is the wavelength. On rearranging the above equation, we get nu is equal to v by lambda. Let this be equation 2. Substituting equation 1 in 2, we get nu is equal to v by 2L by n. By simplifying this equation, we get nu is equal to n into v by 2L. For n is equal to 1, 2, 3, and so on. Let this be equation 3. Equation 3 gives the natural frequencies or the modes of the oscillations of the system. The natural frequencies of a string are integral multiples of the lowest frequency. When n is equal to 1, nu is equal to v by 2L, which is the lowest frequency. The oscillation mode with this lowest frequency is called the fundamental mode or the first harmonic. By taking the values of n equal to 2, 3, and so on, we obtain the second harmonic, third harmonic, and so on. The frequencies associated with these modes are denoted as nu2, nu3, etc. The collection of all possible modes is called the harmonic series, and n is called the harmonic number. A stretched string fixed at both ends can vibrate simultaneously in more than one mode. The mode that is strongly excited depends on where the string is plucked or bored. Musical instruments like the sitar, violin, etc. use this principle to produce music. Let us now study the modes of vibration of a system which is closed at one end and free at the other. The air column in a glass tube partially filled with water is an example of such a system. Vibrations are produced at the open end of the tube with a tuning fork, which travel through the air column in the tube to the water surface and get reflected. This is similar to the reflection of waves in a string that is fixed to a ring and the ring runs up and down the rod without friction. These two waves traveling in opposite directions are in phase. We get an antinote at the open end of the pipe. Let the length of the air column be equal to L. The position of the antinote is expressed as x is equal to n plus 1 by 2 into lambda by 2. Let this be equation 1. For n is equal to 0, 1, 2, 3, and so on represents the positions of the antinodes. Substituting x is equal to L in equation 1, we get L is equal to n plus 1 by 2 into lambda by 2 for n is equal to 0, 1, 2, 3, and so on. By rearranging the above equation, we get lambda is equal to 2L by n plus 1 by 2 for n is equal to 0, 1, 2, 3, and so on. Let this be equation 2. Equation 2 gives the modes which are sustained in the air column. We know that V is equal to lambda into nu, and by rearranging, nu is equal to V by lambda. Let this be equation 3. Substituting 2 in 3, we get frequency nu is equal to V by 2L by n plus 1 by 2. On rearranging the above equation, we get nu is equal to n plus 1 by 2 into V by 2L for n is equal to 0, 1, 2, 3, and so on. Let this be equation 4. Taking n is equal to 0, fundamental frequency nu is equal to V by 4L. Taking n is equal to 1, 2, 3, we get odd harmonics of the fundamental frequency. That is 3V by 4L, 5V by 4L, and so on. The air column open at one end resonates with frequencies denoted by equation 4. When a pipe is open at both ends, there will be antinodes at both ends and all harmonics will be generated. This can be compared to waves produced in a string that is fixed with rings looped to rods at both ends. When a listener hears two sounds of very close frequencies, one after the other with a short time gap, he has to differentiate between them. When both these sounds reach the listener simultaneously, what he hears is the sound of average frequency of the two combined frequencies. The intensity of the sound increases and decreases in slow wavering beats. which have a frequency that exhibits the difference between the two original frequencies. The intensity of the sound wave depends on its amplitude. This phenomenon of wavering of sound intensity, when two waves of nearly the same frequencies and amplitudes propagating in the same direction are superposed on each other, is called beats. Let us understand this phenomenon of beats more clearly with the help of a numerical example. Let the frequency of the first sound wave, nu1, be 256 Hz. And the frequency of the second sound wave, nu2, be 260 Hz. The average frequency of the sound wave heard by the man is equal to 258 Hz. The frequency of the beat, expressed as nu beat, is equal to the difference between nu1 and nu2. On substituting the values of nu1 and nu2 and calculating, we get the value of nu beat is equal to 4 Hz. Let us place these observations into a mathematical expression. Waves 1 and 2 have the same amplitude and phase. The angular frequency of the first wave is greater than the second wave. S1 and S2 are the displacements of a particle from its mean position due to waves 1 and 2 respectively in the x direction at a particular location and time. According to the principle of superposition of waves, S is equal to S1 plus S2. S is the resultant displacement of the particles at a point due to the two waves. Let this be equation 1. We know that S1 is equal to A cos omega 1 into T. And S2 is equal to A cos omega 2 into T. Substituting the values of S1 and S2 in equation 1, we get S is equal to A into cos omega 1 into T plus cos omega 2 into T. This can be written as 2A cos omega 1 minus omega 2 into T by 2 into cos omega 1 plus omega 2 into T by 2. Let this be equation 2. S can be written as A cos omega T, where the amplitude A of the resultant wave is equal to 2A cos omega 1 minus omega 2 into T by 2. And the angular frequency of the resultant wave omega is equal to omega 1 plus omega 2 by 2. Let this be equation 3. In the equation for amplitude A of the resultant wave, the values A omega 1 and omega 2 are constant. As the value of t keeps changing, the value of the cos function also changes. Therefore, the amplitude of the resultant wave is not a constant. This varying amplitude of the resultant wave gives rise to beats. Since the resultant wave is a cosine function, it has maximum amplitude when cos of omega 1 minus omega 2 by 2 into t is equal to plus or minus 1. This implies omega 1 minus omega 2 by 2 into t is equal to k into pi, where k is equal to 0, 1, 2, and so on. From the above equation, t is equal to 2 into k into pi by omega 1 minus omega 2. Substituting the values of k equal to 0, 1, 2, and so on in the equation for t, we get t is equal to 0, 2 pi by omega 1 minus omega 2, 4 pi by omega 1 minus omega 2, and so on. The time interval between any two consecutive maximum values of amplitude gives the beat period t beat of the resultant wave. Therefore, t beat is equal to 2 pi omega 1 minus omega 2. We know that frequency is equal to 1 by time period. Therefore, beat frequency, nu beat, is equal to 1 by t beat. Therefore, by substituting the value of t beat in the above equation, we get nu beat is equal to omega 1 minus omega 2 by 2 pi. Let this be equation 4. We know that omega 1 is equal to 2 pi nu 1 and omega 2 is equal to 2 pi nu 2, where nu 1 and nu 2 are the frequencies of waves 1 and 2 respectively. Substituting these values in equation 4 and simplifying, we get nu beat is equal to nu 1 minus nu 2. Similarly, let's calculate the beat frequency when the amplitude of the resultant wave is 0. Amplitude A is minimum when cos omega 1 minus cos omega 2 by 2 into t is equal to 0. This implies that omega 1 minus omega 2 by 2 into t is equal to 2k plus 1 into pi by 2, where k is equal to 0, 1, 2, and so on. From the above equation, T is equal to 2k plus 1 into pi by omega 1 minus omega 2. Substituting the values of k is equal to 0, 1, 2 and so on in the equation for t. We get t equal to pi by omega 1 minus omega 2. 3 pi by omega 1 minus omega 2. 5 pi by omega 1 minus omega 2 and so on. Beat period t beat is the difference between two consecutive values of t. Therefore, t beat is equal to 2 pi by omega 1 minus omega 2. Therefore, beat frequency, new beat, is equal to 1 by t beat, which is equal to omega 1 minus omega 2 by 2 pi. Substituting and simplifying the values of omega 1 and omega 2 in the above equation, we get new beat is equal to nu 1 minus nu 2. Therefore, the beat frequency, new beat, when amplitude is maximum or minimum, is the difference between nu 1 and nu 2. Musicians use the beat phenomena to tune their instruments. The musical instrument is sounded against a standard frequency and tuned until the beat disappears.